Hey everyone, and welcome to The Explainer. I am so incredibly thrilled to have you here today. We are going to explore the absolutely fascinating world of acids, bases, and salts. Whether you're encountering these concepts for the very first time, or you're just here to solidify your foundation for an upcoming exam, we're going to break down exactly how these chemicals interact, how they react, and how they transform. Okay, let's dive right into it.
Here is the roadmap for our learning journey today. 1. Objectives and core concepts. 2. Strong versus weak acids. 3. Acids, bases, and metals. 4. Metallic oxides and acids. 5. Non-metallic oxides and bases. And finally, 6. Misconceptions and a final review.
All right, Section 1, Objectives and Core Concepts. Let's get our foundation set.
Think of chemistry like building a house. You really can't build a sturdy roof without a solid foundation, right? Understanding basic ionization, literally just how molecules break apart in water, is going to unlock the secrets to the much more complex oxide reactions we'll tackle later in this explainer. So keep this hierarchy of concepts in the back of your mind as we progress. Everything connects.
Section 2, Strong versus Weak Acids. Let's talk about how they behave in water. So what actually makes an acid strong or weak? It's funny. It actually has nothing to do with how dangerous it is or if it'll burn a hole in the floor. It has everything to do with how it behaves in water. When we talk about strong acids, we mean they completely ionize in water. Every single molecule breaks apart to produce hydrogen ions or H+. On the flip side, a weak acid is only partially ionized. It produces a much smaller amount of those hydrogen ions or hydronium ions per unit volume. I want you to visualize those ions in your head, either completely shattering apart all at once or just a stubborn few breaking off.
Let's run through some specific examples. In the strong acid category, we have the heavy hitters, the ones you see in the lab: hydrochloric acid, sulfuric acid, and nitric acid. These completely ionize. But then look at the weak acids. You might actually recognize some of these from your own kitchen. We have citric acid, which is exactly what gives lemons that bright sour taste, and acetic acid, which is the main component of vinegar. We also have carbonic acid and formic acid here. Because they only partially ionize, their chemical behavior is entirely different.
Moving right along to Section 3, Acids, Bases, and Metals. It's time for some actual reactions.
So what happens when we drop active metals into these solutions? Well, when an active metal, let's say zinc, reacts with an acid like hydrochloric acid, it displaces the hydrogen to form a salt, in this case zinc chloride, and it releases this amazing, glowing hydrogen gas. But here's where it gets really interesting. Bases can also react with some metals, like zinc, to produce salt and hydrogen gas. For example, sodium hydroxide plus zinc gives us hydrogen gas and sodium zincate. Now, it's absolutely crucial to remember that bases generally don't react with metals in the same widespread way that acids do, and the products they form, like sodium zincate, are much more complex compounds.
Okay, red flag time. Here is a major trap you need to avoid on test day. Not all metals react with acids. I repeat, not all metals. It requires an active or highly reactive metal to displace that hydrogen. If a metal is less reactive than hydrogen, it simply won't have the chemical power to kick the hydrogen out of the acid molecule. Always check your reactivity series.
Section 4, Metallic Oxides and Acids. We are leveling up the complexity by bringing oxygen into the mix.
Before we jump into the formulas, I want you to pause and just actively think about this. If we take an acid and we react it with a metallic oxide, which is just a metal bonded to oxygen, what do you think the resulting products will be? Any guesses?
If you guessed salt and water, you nailed it. Absolutely right. We actually call these metallic oxides basic oxides. Why? Because when they react with acids to form a salt and water, they are behaving exactly like a base does during a classic neutralization reaction. Let's look at how these formulas play out. When copper 2 oxide reacts with hydrochloric acid, we get copper 2 chloride, which is our salt, and water. And the exact same pattern holds true for aluminum oxide reacting with hydrochloric acid to give us aluminum chloride and water, or zinc oxide reacting with sulfuric acid to yield zinc sulfate and water. It's so consistent. The metal oxide and the acid constantly team up to neutralize into salt and water.
Section 5, Non-Metallic Oxides and Bases. Let's flip the script.
So if metallic oxides act like bases, you might logically guess that non-metallic oxides act like acids, right? And in a lot of cases, you'd be totally right. Take a look at this reaction. We have calcium hydroxide, a base, reacting with carbon dioxide, which is a non-metallic oxide. And the result?
we get calcium carbonate, which is a salt, and water. Because the carbon dioxide is neutralizing the base, it is literally exhibiting acidic behavior.
And carbon dioxide isn't the only one that pulls this trick. Sulfur trioxide and phosphorus pentoxide are also brilliant examples of non-metallic oxides that react with bases to form salts. Because of this, we can confidently classify these specific compounds as acidic oxides.
Finally, Section 6, Misconceptions and Final Review. Let's make sure we don't fall for any tricky generalizations.
We need to bust a pretty huge misconception right here. Because carbon dioxide acts as an acid, it is super easy to just assume that all non-metallic oxides are acidic. But the scientific reality is a bit more nuanced. Non-metallic oxides can actually be acidic, basic, or entirely neutral. For instance, silicon dioxide and carbon monoxide are totally neutral. They simply do not react with acids or bases at all. You definitely want to remember these neutral exceptions.
Let's lock this all into our memories. Here are your core rules of thumb from today's explainer. First, an active metal plus an acid gives you a salt and displaces hydrogen gas. Second, a metallic oxide plus an acid gives you a salt and water, meaning the metallic oxide is acting as a base. And finally, a non-metallic oxide plus a base gives you a salt and water, often acting as an acid. But remember, always keep an eye out for those sneaky neutral exceptions.
You've got a seriously powerful understanding of these chemical interactions now. So I want to leave you with this final thought. Knowing how these neutralization reactions happen conceptually, how do you think scientists and engineers can apply these exact formulas to treat massive real-world problems? I mean, things like neutralizing acid rain in our lakes, or fixing highly acidic soil for farmers so crops can actually grow. Think back to the basic oxides we learned about today. Chemistry isn't just something that lives on a chalkboard. It's the exact tool we use to heal the world around us. Keep exploring, keep asking questions, and I'll see you in our next explainer.